Hi there, my name is Nepotistically, and in this talk I'll be presenting our paper titled Nepotistically Trained Generative Image Models Collapse, which is published at an ICLR workshop. This is joint work between myself and Professor Hani Farid. I want to motivate this work by talking a bit about the AI ecosystem in which we find ourselves these days. If you think about any generative AI image model, think DALL-E, Stable Diffusion, Flux, etc., you'll find that most of these were trained on data scraped from the internet. And it's really the scale of the internet that enables these models to achieve the kinds of photorealism and generalization that we see in these models. Now, as these models became really good, people started noticing, and many users began generating images and sharing these images with others online to spread best practices with prompts and just kind of showcase their work. And quickly this became much broader and much bigger than just a niche for techies online. And so these images began being uploaded back to the internet. Now, for any new iterations of training, that created a potential issue, because now in this domain, in this distribution of images on the internet, it was no longer just real images or real paintings or real art. It was all of a sudden real images, real art, but also AI images. And that could potentially create issues. And so we wondered, what happens when a generative image model is trained on its own generations? And that's really the question that we explored in this paper. So to answer this question, we ran a series of experiments in which we continued training, we resumed training or fine-tuned an off-the-shelf diffusion model, in particular Stable Diffusion 2.1, and we were at the training inserting different levels of AI generated images that this model itself produced. In this plot, in this figure right here, I'll be showing different qualitative results, and by qualitative, this is a representative image produced based on the prompt photo of a middle-aged Hispanic man, and I'll be increasing the level of poison, where poison refers to the percentage of AI images in the training set, and you'll see how this changes over epochs of fine-tuning or epochs of retraining. So to start, let's just see what the results are for a healthy model with no poisoning. You'll see that these images are indeed photorealistic and are pretty diverse, and so they correspond to the prompt, or they look as desired. Now, if I increase poisoning to 10%, you'll notice that these images start evincing different attributes that are not desired in these images. And the further we go in this fine-tuning, the more undesirable effects start appearing in these images. And these evince what we call model collapse in these models. Now I can increase the poisoning even further, and notice that it's not only the quality that decreases as poisoning increases, but it's also the diversity that decreases as the poisoning increases. And you see this more and more as we progress in the poisoning, all the way down to 100%, where after 5 epochs, the image or the model fully collapses. With these results, we wondered how much data needs to be poisoned for this collapse to occur. And we found that even when you have only 3% of the training set poisoned, you'll still find undesired artifacts that are resembling the kinds of artifacts we saw on the previous slide with the model collapse. Now, to be a bit more quantitative, here I'm showing 2 different metrics of synthesis quality for these poison models. At the top, we have the fresh at inception distance, FID, where higher means worse, it's more distant from some benchmark, and lower means better. And at the bottom, we see the clip score figure, where higher is the opposite. Higher means better, and lower means worse. These lines or these curves represent different models at different poisoning rates, and you see that the healthy model stays the same, stays healthy, but the poison models decrease in their performance. Now, having seen these results and kind of confirmed quantitatively our qualitative results, we wondered, can the models heal? And by healing, we mean, can they go back to their pre-poisoning state? And so to test this, we essentially resumed training after this 5th poisoned epoch, but now again with only healthy images. So again with no AI images and only real images in the training set. And you'll see that the models do indeed heal, and they do get back to near pre-poisoning performance. So to summarize, we saw and we demonstrated that when a generative image model is trained on its own generations, it collapses. And this happens with as little as 3%. We also tested whether the model can heal, and we found that yes, it can to some extent. However, it does take time, and it gets to near pre-poisoning performance. Now, what are the implications of this work? We believe that there is a story about the incentives of the labs or companies that produce these AI models, that train these AI models. And in particular, we believe that in order for them to maintain a certain quality of these models, it is in their best interest to actually be able to distinguish between real and AI generated images. And that aligns with the incentives or some of the goals of folks in the forensics and trust and safety communities. What's also desirable would be a way of auditing whether a single or sets of images were used to train a model post hoc. Thank you so much, and we are looking forward to seeing you at ICLR.